Here is the message planned into segments in space, or like a surface, like a versatile trampoline net. Change this trampoline net into a pretzel and allow yourself to go backward in time. We had the choice to go from Earth to the Moon, across 250,000 miles of space, land on the Moon, and then return to Earth. This was due to Newton's understanding of gravity. Albert Einstein, the remarkable physicist, once said that gravity is a deception. Einstein had committed his career to uncovering the reality of gravity, refuting Newton's widely held beliefs, and addressing perplexing time travel questions. Why is there only one way in which time travel exists when you travel at the speed of light? Why does time slow down? The latest theories and discoveries by modern physicists attempt to provide an ultimate theory of time to explain the unexplainable. Newton's gravity hypothesis. People didn't begin to seriously question their surroundings until the 1500s. The ancient Greeks believed that gods and divinities could explain and sustain everything. However, by the 1500s, scientists like Galileo and Brahe had established that Earth was a planet, not the center of everything. The planets in our solar system orbited the Sun. Kepler went a step further, describing how planets and their moons moved along their axes in an elliptical, not a perfectly circular, orbit. Newton followed in the 17th century. The world knows about the English physicist who supposedly stumbled upon gravity after an apple fell on his head. However, it is now accepted that Newton didn't simply discover the theory of gravity. For a long time, he had been observing still objects shift from their constant positions due to some unexplained force. Yes, this also involved seeing apples fall from trees. After hours of study, Newton finally proposed that this attractive force was gravity. He was also able to advance Kepler's elliptical orbit hypothesis due to this discovery. The Moon, the nearest celestial body to Earth, can orbit the planet because of a straight-line tangent that crosses Earth's center, holding the Moon in place under the planet's gravitational pull. Einstein and his theory of relativity. Before Brian Cox challenged Newton's theories, there was Albert Einstein. The renowned physicist didn't explicitly disprove gravity but declared that Newton's ideas were one-dimensional. Einstein's general theory of relativity suggested that work and space twist, leading to gravity. He further defined the fabric of spacetime as a sheet where weight exceeds a threshold. Einstein also claimed that a clock placed inside Earth's gravitational field would run slower than one outside its orbit. Gravity, he demonstrated, exists between any two objects, whether planets in orbit or marbles on a tabletop, and is governed by the inverse square law. According to this law, gravity is inversely proportional to the square of the distance between two objects and directly related to their masses. Einstein's ideas extended to time. He argued that the laws of physics apply to everyone not traveling faster than light. Space and time are essentially the same, the space-time continuum, and gravity results from a warp in this continuum. Modern perspectives. Brian Cox. Though Newton is considered one of the greatest physicists, contemporary scientists like Brian Cox note that Newton didn't fully define gravity. Cox argues that Newton only attempted to explain a basic concept already widely understood and accepted. One reason for this limited exploration could be the dominance of religion over science in Newton's era. A religious man himself, Newton avoided developing the theory further, attributing gravity to a sentient entity controlling planets and the solar system, challenging physics and gravity. To challenge gravity and physics, one must challenge existing norms. Applications of time dilation. Time dilation, defined by the theory of special relativity, demonstrates that a moving clock in an inertial frame ticks slower than a stationary clock. This principle could push time travel into possibility. For instance, travelers in a high-speed vehicle could reach their destination a few seconds earlier than those stationary. Experiments conducted on the International Space Station, ISS, showed that astronauts experienced a 20-millisecond delay in time due to their high velocity. Einstein used the concept of a light clock to describe relativity, where a light beam travels in a straight line. To an observer at rest, the light beam seems to cover a greater distance. Einstein argued that the speed of light is constant regardless of motion. Therefore, time is not absolute, it can stretch or contract based on conditions. Practical applications. Einstein's theories have led to practical applications, such as GPS navigation. GPS systems exchange signals between devices and satellites orbiting Earth. These satellites in space experience time dilation due to weaker gravitational forces. Relativity suggests that time is not an absolute construct but a relative experience influenced by speed and gravity. This leads to mind-boggling possibilities such as time travel and variations in event perception, depending on the observer's frame of reference. The twin paradox. One of the most famous thought experiments derived from Einstein's theory is the twin paradox. Imagine two twins. One remains on Earth while the other travels at nearly the speed of light into space. Upon returning to Earth, the traveling twin would have aged far less than the twin who stayed behind. This paradox demonstrates how time dilation works at extreme speeds. While fascinating, this concept remains largely theoretical, as humans cannot yet travel at the speeds required to observe this phenomenon on a large scale. Length contraction. Another implication of relativity is length contraction, which states that objects moving at high speeds appear shorter along the direction of motion to a stationary observer. For example, a race car speeding by at an incredible velocity may appear slightly smaller than it truly is. If we could observe an object moving at the speed of light, the degree of contraction would be much more dramatic. This effect, though subtle in daily life, is crucial in understanding high-speed phenomena in physics. Practical uses of relativity. Apart from GPS navigation, other applications of Einstein's theories include 1. Particle accelerators. High-speed particle accelerators rely on relativistic physics to understand how particles behave at nearly the speed of light. These studies have led to groundbreaking discoveries in particle physics, including the Higgs boson. 2. Astronomy. Einstein's general relativity is fundamental in modern astronomy. It explains the behavior of black holes, gravitational waves, and the expansion of the universe. The detection of gravitational waves by LIGO in 2015 directly confirmed predictions made by Einstein a century earlier. 3. Nuclear energy. The famous equation explains the massive energy released in nuclear reactions. This principle underpins both nuclear power generation and atomic weaponry. 4. Timekeeping. Atomic clocks, the most precise timekeeping devices, account for relativistic effects caused by gravity and motion. These clocks are essential for global communication networks, scientific research, and navigation. Pushing the boundaries of spacetime. Physicists continue to explore the mysteries of time, gravity, and the universe. Theories such as string theory, quantum gravity, and the multiverse attempt to unify general relativity with quantum mechanics. While these ideas remain speculative, they challenge our understanding of reality and open doors to revolutionary advancements. Can we travel through time? Time travel remains one of humanity's greatest fascinations. While special and general relativity suggest it might be theoretically possible under specific conditions, e.g., wormholes or near-light speed travel, practical implementation faces immense challenges. 1. Energy requirements. Traveling near the speed of light or creating a wormhole would require an enormous amount of energy, far beyond current technological capabilities. 2. Causality paradoxes. Time travel presents paradoxes, such as the famous grandfather paradox, where a traveler could potentially alter the past and affect their own existence. Resolving these paradoxes would require new laws of physics. 3. Stability of wormholes. If wormholes exist, they would likely be unstable and prone to collapse. To stabilize a wormhole for time travel, exotic matter with negative energy density would be needed, a substance that is purely hypothetical at this time. Final thoughts. Einstein's revolutionary ideas reshaped our understanding of the universe, challenging us to think beyond our everyday experiences of space and time. While some concepts, like time travel, remain in the realm of theory, their exploration pushes the boundaries of science and human imagination. Who knows? Perhaps one day, advancements in technology and physics will turn these mind-bending ideas into reality, forever altering how we perceive and interact with the universe. The importance of relativity in everyday life. Einstein's theories are not only revolutionary in the world of theoretical physics, but also essential for the functioning of modern technology. Imagine, for a moment, that special relativity had never been explained. Without an understanding of relativity, precise navigation systems like GPS would not exist, or if they did, they would be wildly inaccurate. Satellites must account for time dilation caused by both their high velocity and the weaker gravitational forces in space compared to Earth's surface. These adjustments, based on special and general relativity, allow GPS systems to reliably measure time differences and provide accurate location data. It's hard to imagine a world without navigation systems, and the reason we have them today is that organizations launching satellites into space factor in relativistic effects to ensure their functionality. The general theory of relativity. Nearly a decade after publishing his theory of special relativity, Einstein introduced the general theory of relativity in 1915. This theory proposed that gravity is not a force acting at a distance, as Newton believed, but rather a curvature of spacetime caused by massive objects. How general relativity explains gravity. 1. Spacetime curvature. Massive objects, such as planets or stars, cause spacetime to curve around them. This curvature directs the paths of other objects, creating the effect we perceive as gravity. For example, the Earth orbits the Sun not because of an invisible force, but because the Sun's mass creates a dent in spacetime, guiding Earth's motion. 2. Time dilation in gravitational fields. According to general relativity, time flows more slowly in stronger gravitational fields. This phenomenon, known as gravitational time dilation, has been confirmed through experiments, such as the use of atomic clocks placed at different altitudes. Clocks closer to the Earth's surface, in a stronger gravitational field, run slightly slower than those at higher altitudes. Practical implications of general relativity. 1. Black holes. One of the most fascinating predictions of general relativity is the existence of black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. Observations of black holes, including the first-ever image captured in 2019, confirm Einstein's predictions. 2. Gravitational waves. In 2015, scientists at LIGO detected gravitational waves for the first time, ripples in spacetime caused by massive events like the collision of black holes. This groundbreaking discovery was a direct validation of Einstein's century-old predictions. 3. The expanding universe. General relativity also supports the idea of an expanding universe, first observed by Edwin Hubble in the 1920s. Einstein's equations laid the foundation for understanding cosmic expansion, dark energy, and the Big Bang theory. The future of time, space, and gravity. Physicists continue to explore theories that push the limits of our understanding of the universe. Concepts such as string theory, quantum gravity, and the multiverse aim to unify Einstein's relativity with quantum mechanics, bridging the gap between the very large, cosmos, and the very small, subatomic particles. While these ideas remain largely theoretical, they inspire new experiments and technologies that may one day unlock deeper truths about time, space, and gravity. Time travel, a dream or reality. Time travel, though popular in science fiction, remains a tantalizing but elusive goal in physics. Here's a summary of the challenges and possibilities. 1. Theoretical possibilities. Wormholes, hypothetical shortcuts through spacetime that could, in theory, allow for time travel. However, they require exotic matter to stabilize and are purely speculative at this stage. Near light speed travel. Traveling at speeds close to the speed of light could theoretically allow for time dilation, enabling a form of forward time travel. 2. Technological and energy barriers. Achieving the energy levels required to create a wormhole or accelerate a spacecraft to near-light speeds is currently beyond our technological capabilities. 3. Causality paradoxes. Time travel raises logical paradoxes, such as the grandfather paradox, where altering the past could create inconsistencies in the timeline. Resolving these paradoxes would require new insights into the laws of physics. Final reflections. Einstein's work on relativity transformed not only physics but also our understanding of reality itself. Concepts like spacetime curvature, gravitational waves, and time dilation have reshaped how we view the universe and our place within it. While time travel and other futuristic ideas remain theoretical, the pursuit of these concepts inspires human innovation and curiosity. Who knows what discoveries await in the centuries to come?